You've seen trains speeding across countries and hauling massive loads. But have you ever wondered what it really takes to build one? From raw steel to roaring engines, the process is bigger, louder, and more precise than you think. In this video, we're pulling back the curtain to show you how today's trains are truly made, from the very first weld to the final test run. Stay with us, because by the end, you'll never look at a train the same way again. The birth of trains. Before the age of locomotives, the world moved at the speed of a horse, a sail, or a current. But the Industrial Revolution changed everything. People wanted faster, more powerful ways to move goods and people. And in the early 1800s, inventors had one bold idea. What if machines could ride on metal tracks? That idea took real shape with George Stephenson, the man known as the father of railways. In 1829, his locomotive, the Rocket, became the first full-scale working steam train to haul passengers and goods at an impressive 30 miles per hour. It ran on a track in northern England, and it didn't just move coal, it moved history. The early goal of trains was simple: move more stuff, faster, with fewer people, but it quickly became so much more. Trains connected cities. They changed how armies moved. They even transformed the layout of towns, giving birth to the modern commuter lifestyle. As Stevenson once said, the rage for railways is such that there is no stopping it. And he was right. Within decades, railroads circled the globe, and the train became a symbol of progress. But those first trains were just the beginning. The machines would get bigger, stronger, and faster, reshaping the world even more as they evolved. The evolution of trains. In the beginning, trains ran on steam, giant iron beasts hissing and roaring across the countryside. They were powerful but demanding, needing constant coal and water and frequent maintenance. Steam engines were loud, slow to start, and messy. But for the 1800s, they were a miracle. As time went on, engineers and inventors kept improving the technology. In the early 20th century, steam began to step aside for something cleaner and more efficient: diesel and electric locomotives. These machines could run longer distances, required less upkeep, and could be controlled with more precision. And with that, trains took on new identities. Some were built for speed, like Japan's famous Shinkansen bullet trains. Others, like North America's freight locomotives, were designed purely for brute strength, pulling massive loads across mountains and deserts. Even today, train technology continues to evolve. Modern locomotives are smarter than ever. Many are fitted with GPS, onboard diagnostics, and even automatic braking systems. They're also more environmentally friendly, using fuel more efficiently and reducing emissions. As railway historian Christian Wolmar put it, the train may be old technology, but it keeps reinventing itself better than anything else. And that reinvention led to many different kinds of trains, each one built for a different mission. Not all engines are created equal. When you picture a train, what do you see? A bullet-speed passenger train racing across the countryside? Or a slow, rumbling giant hauling containers? The truth is, not all trains are built the same. Passenger locomotives are designed for speed. They're lighter, more aerodynamic, and engineered to glide across rails for long distances with minimal drag. They serve commuters and travelers, getting people from city to city, coast to coast. On the other hand, freight trains are the muscle of the railway world. North America's heavy haul units, for example, are massive, some weighing more than 200 metric tons and pulling over a kilometer of cargo cars. These are made for endurance, not speed. Then there are yard locomotives, smaller machines used to move rail cars around in train yards and local areas. They're like the forklifts of the railway: quiet, nimble, and incredibly useful. The technology behind each type varies depending on geography, too. In Europe, trains are often compact, designed for tight curves and strict regulations. In North America, broader tracks allow for bigger, heavier builds. As one rail engineer once put it, "Tell me what you need to move, and I'll tell you what kind of train to build." That decision starts at the foundation, the literal base of the locomotive, building the underframe. Every train starts with a frame, not a blueprint, a real solid steel underframe, welded by hand and machine to form the skeleton of the locomotive. It's the first thing to be built, and everything else depends on its strength. To begin, workers weld thick steel beams into a massive rectangular base. This underframe has to handle incredible weight, up to 454 metric tons. At each end, a large steel pivot pin is inserted. These pins will eventually connect the underframe to the bogies, the wheel sets that make trains roll. At this stage, automated welders take over. They move in circles around each pin, slowly building up a thick 2.5 centimeter weld that secures the connection. Every seam is reinforced, every joint checked, because failure here isn't an option. Then, using massive cranes, the underframe is flipped upside down and welded from the opposite side. It's precision work, done on a gigantic scale. As one fabricator puts it, it's like building a tank that can sprint. But tanks don't move without fuel, and that's where the next stage begins. Installing the fuel tank and brake system. With the frame built and ready, the next step is installing the systems that power and protect the locomotive, starting with the 20,000-liter fuel tank. That's enough diesel to keep the train running for hundreds of miles without stopping. Right alongside it is the pneumatic brake system. Unlike cars, which rely on hydraulics, trains use compressed air to activate the brakes. It's safer, stronger, and works across dozens, sometimes hundreds, of connected cars. These systems are installed beneath the underframe. They're not flashy, but they are essential. The fuel tank is what gives the train its range. The brakes are what give it control. Put simply, one makes the train unstoppable, the other makes it stoppable. As one railway technician said, a train that can't go is useless, but a train that can't stop is a disaster. And now that the frame, fuel, and brakes are in place, it's time to bring the real muscle on board. Building the traction motors. Now that the base and inner systems are set, it's time to give the locomotive its heartbeat, its traction motors. These aren't like the engines in your car. They're much stronger, much heavier, and built to survive the most demanding industrial conditions on Earth. Each locomotive has 6 traction motors, and every single one produces about 750 horsepower. That's 4,500 horsepower in total, enough to pull hundreds of loaded freight cars across mountains, deserts, or icy plains. The process starts by winding copper coils into a thick steel ring called a stator. This becomes the outer shell. Then, a cylindrical piece, known as an armature, is lowered into the center. Once electric current is introduced, generated by a powerful alternator, it creates a magnetic field. That magnetic force spins the armature, and that spin creates motion. This isn't just electrical magic, it's precision engineering. The better the alignment, the smoother the torque, the more efficient the power. These motors are what actually drive the train's wheels. Without them, even the strongest diesel engine would be powerless. In the words of one train builder, the traction motor is where raw energy meets motion. It's what makes a train come alive. But a spinning motor isn't useful unless it turns something real. And that brings us to the next critical piece of the puzzle, the Wag Assembly. Once the traction motors are built and ready to generate power, that raw rotational force needs a way to meet the tracks. After all, you can create all the energy in the world, but unless you can convert it into forward motion, you're going nowhere. That's where the WAG comes in. WAG stands for Wheel Axle Gear Assembly, and it's the crucial bridge between the spinning motors and the rolling steel wheels that carry the train across continents. Without the WAG, the locomotive would just be a humming, stationary giant. With it, that power finally touches the ground, literally. The assembly starts with a massive axle forged from hardened steel to withstand unimaginable stress. It needs to be strong enough to support 2 wheels, each weighing over 1,000 pounds and measuring about 1 meter in diameter. These wheels are forged from a special alloy steel that can resist not only wear and tear, but also extreme friction and temperature changes caused by high-speed operation. The wheels are then press-fitted onto either end of the axle using an industrial machine that applies thousands of pounds of force. No bolts, no adhesives, just sheer pressure holding them in place. Why? Because even the smallest slip could lead to disaster at full speed. This process ensures absolute stability. Once mounted, the wheels and axle become a single solid rotating unit. Next comes the gear system. Each axle has a large, precision-machined gear mounted at its center. That gear directly engages with the gear from the traction motor. So when the motor spins, it turns its own gear, which then meshes with the gear on the axle. That torque is instantly transferred to the wheels. And just like that, motion is born. This isn't just engineering, it's choreography. Every tooth on every gear must align perfectly. Every rotation timed to the millisecond. A misalignment here would create noise, vibration, and ultimately, failure. 6 of these WAG units are built for each locomotive, 1 per traction motor. Once they're finished, they're divided into 2 symmetrical sets of 3. These 2 groups will eventually be mounted into the bogies, forming what engineers often call the legs of the locomotive. As one veteran rail engineer put it, if the traction motor is the muscle, then the WAG is the foot. It's what touches the earth. It takes all that power and makes it real. But of course, even the strongest legs need structure and balance. That's where bogies come in, the next critical step in making this steel beast walk. Assembling the bogies. Now it's time to give the train its footing. Those Wag assemblies are mounted into massive metal frames known as bogies, the sturdy wheel carrier structures that sit beneath the train. Each bogie holds 3 axles, meaning 3 Wag units per bogie. It also houses a full braking system and its own suspension setup, allowing the train to absorb shocks and stay stable over uneven tracks. These bogies are not just wheel holders, they're full systems in themselves. Interestingly, the bogies are built upside down at first. That's because it's easier to install the heavy parts and connect brake lines when the whole unit is flipped. Once the wiring and gear alignments are completed, a crane carefully flips them right side up. With that final turn, the bogies are now ready. They're complete, tested, and waiting to carry the massive frame of the locomotive. Or as one assembly worker says with a grin, "We just gave this beast its shoes." Now that the feet are ready, the frame is complete, and the power systems are standing by. It's time to bring it all together, connecting bogies to the underframe. Now comes one of the most dramatic and delicate steps in the entire build, connecting the bogies to the underframe. This is more than just a mechanical task. It's the moment when all the separate parts finally become one machine. It's when the scattered bones of steel, wire, and wheels begin to stand tall and take form. In this moment, the train becomes real. It starts with precision and patience. Using massive overhead cranes, workers carefully move the 2 bogies, those massive 3-axle wheel frames, into position beneath the underframe. Each bogie is loaded with braking systems, traction gear, and suspension components, all pre-assembled and tested. They have to sit just right. Millimeter precision is key. Then the underframe, now weighing tens of thousands of pounds, is slowly, almost imperceptibly lowered inch by inch. Workers guide it from the ground, watching like surgeons in an operating room. The goal? To drop the pivot pins located at either end of the underframe into the receiving holes on the bogies with perfect alignment. These pivot pins are no small feature. They're giant steel connectors, engineered to carry unimaginable stress while still offering flexibility. Once secured, they allow the locomotive to bend gently through curves, absorbing lateral movement without compromising the train's structural integrity. It's a unique blend of strength and subtlety, one that lets a 200-ton machine glide along twisting tracks with grace. When both bogies are in place and connected, the transformation is immediate. What was once just a heavy frame is now a rolling structure. It stands tall, it moves, it has mass and purpose. But this isn't just a structural moment. It's deeply symbolic. As one team leader on the factory floor once put it, when the bogies touch the frame, it's like the body getting its spine. Everything comes to life. After the connection is made, the real work begins again. Engineers move in to verify mechanical integrity and alignment. Every gear that connects to the traction motors is inspected. Brake lines are pressure tested. Electrical cables that run through the bogie channels are hooked up and checked for continuity. Suspension components are monitored for stress points. The entire system is walked, reviewed, tightened, and scanned. This stage marks the first time the locomotive can physically support its own weight, and potentially roll forward under power. It's a powerful moment, not just in terms of mechanics, but in the emotional rhythm of the build. With the frame now locked to the bogies and the spine firmly in place, the machine is ready for its next milestone, installing the beating heart that will bring thunder to its steel veins. The engine is next, and when it drops in, the locomotive's true power will finally awaken. Engine and alternator installation. The final step in powering the locomotive is installing the diesel engine and the alternator. Together, they form the energy center of the entire train. First comes the 16-cylinder diesel engine, a monster of a machine that weighs several tons and delivers all 4,500 horsepower needed to move the train. This engine doesn't power the wheels directly. Instead, it spins a high-capacity alternator mounted beside it. The alternator's job is to convert mechanical energy into electricity. That electricity then travels to the 6 traction motors and powers them individually. It's a hybrid design, diesel-powered but electric-driven. On top of that, the alternator also supplies power to auxiliary systems, lighting, climate control, computer systems, even external hookups for other cars. This setup, engine plus alternator, is what makes modern trains so efficient. They can start, stop, reverse, climb hills, and haul over a kilometer of way without missing a beat. As one mechanic described it, this isn't just an engine, it's a generator, a power station on wheels. With the engine locked in and humming, there's only one thing left to do: give the machine its mind and finish the build. Operator's cab setup. If the engine is the locomotive's heart, then the operator's cab is its brain. This is where every command is made, every system is monitored, and every journey begins. It's not just a driver's seat, it's a high-tech command center on rails. The cab is lowered onto the underframe near the front of the locomotive. But before it's fastened down, it's outfitted with everything a modern engineer needs: sound insulation, shock absorber mounts, and climate control. Because the cab doesn't just need to function, it needs to survive rough weather, constant vibrations, and long hauls across every terrain imaginable. Inside, you'll find multiple display screens, analog backup gauges, and physical controls for braking, throttle, and emergency stops. There are computer systems that track fuel consumption, engine diagnostics, GPS positioning, and even predictive maintenance alerts. Some cables feeding into the cab are so thick, they look more like fire hoses, each carrying up to 10,000 amps and housing thousands of tiny wires bundled together. This cab is built for endurance. For operators who may be in this cockpit for 10-12 hours at a time, it has to be safe, quiet, and efficient. There are even blackout blinds for nighttime operations and emergency override controls in case something goes wrong. An engineer once said, "When you sit in the cab and start that engine, it's not a train, it's a living thing, and you're in charge of it." Now that the brain is in place, all systems are connected. There's only one step left: put the finishing touches on the machine and prepare it for life on the rails. Final assembly and testing. With all the major parts in place, the frame, the engine, the cab, the bogies, the locomotive now looks like a finished machine. But before it can go anywhere, it still has to prove it can survive the journey. First, a protective hood is installed over the engine and alternator to shield them from rain, snow, and flying debris. This hood also helps with heat insulation and houses the locomotive's external vents and exhaust system. Next, the entire machine is wired, sealed, and waterproof buffed. All brake lines, fuel lines, power cables, and electronics are checked, tested, and rechecked. No screw is too small, no bolt left unchecked, because in the real world, trains can't afford breakdowns. Then comes the most critical part: the test bay. Here, the locomotive is powered on for the first time. Its systems are monitored as it goes through braking simulations, load tests, and electrical diagnostics. The alternator is tested under full engine load. The traction motors are run through high and low speed cycles. Lights, horns, warning signals, and backup systems are all activated. If anything's off, no matter how small, the locomotive goes back for adjustments. Only once it passes every test is it cleared for the final step: paint and decals. It's here where the machine takes on its identity, whether it's the bold yellow of Union Pacific, the red of Canadian Pacific, or the electric blue of a European line. As one final inspector put it, the tests don't lie. If it rolls out of here, it's ready for anything. But before it hits the tracks, there's one more story to tell. What these machines are truly built for. From factory floor to Freight King, the final product. And now the locomotive is ready. It's nearly 23 meters long, weighs over 200 metric tons, and is built to operate in freezing mountains, scorching deserts, or endless plains. Fueled up and fully powered, it's ready to haul over a kilometer of cargo or passengers, depending on its configuration. Each locomotive that leaves the factory represents thousands of hours of planning, welding, testing, and engineering. From the moment the first steel beam was welded to the second the engine roared to life, every step was about durability and precision. This machine isn't built to sit in a showroom. It's built to run, non-stop, day and night, for decades. Modern freight trains in North America often operate for over 1 million miles in their lifetime. Passenger versions, especially high-speed trains, are maintained like airplanes, routinely inspected, upgraded, and rebuilt to keep pace with ever-changing tech. What started as a simple idea in the early 1800s to move faster than a horse has become one of humanity's most advanced transportation systems. Trains are no longer just steam-belching engines. They're high-tech, eco-conscious, data-driven giants. In the process of building one that is nothing short of a mechanical symphony. As one senior technician said while watching a locomotive roll off the line, "You don't build a train, you build a future that runs on steel." And that's how a powerful, high-tech train goes from blueprint to full-speed reality. If you enjoyed learning how these giants are built, give the video a like, hit subscribe, and tap the bell so you don't miss more stories like this. Thanks for watching. We appreciate having you on board.